Now we're boiling this water and we're going to try and put this bowl into the water, the hot water, and we're going to see what happens. We're going to let it stay this way for a few minutes.
The first thing we are going to do today is observe the expansion of metals. And Khalila, why don't you describe our first experiment?
Sure. Here we have a ring and a bowl. See here we have put this into a room temperature water originally because we want this the bowl and the ring to be at equal temperature so that our experiment could be accurate. Now here, as you can see, the bowl can easily slide through the ring. This is because the outer surface of the bowl is almost equal to the inner surface. The outer surface diameter of the bowl is almost equal to the inner diameter of the ring. But they're not equal because if they were equal, the ball would not be able to pass through it. So there's always a slight gap for it to be able to pass through it. Now what we're gonna do is first we're gonna hit the ball and then we're gonna see the effect of it. So I want you guys to give me different hypotheses on what you think would happen if I hit the ball. And I would not be hitting the ring, just the ball.
Okay. I think it will expand, and it will expand in both sides. So I don't think it will come through.
Okay. Does anyone else have a different ideas?
I think it will stay the same.
The same. Okay. And Malik, do you have a different idea?
I think the ball will be able to pass through the ring.
Would it stay the same or would it shrink?
Maybe it will shrink.
Okay, then the best way to see this is if we try it, right? Now we're boiling this water and we're going to try and put this bowl into the water, the hot water, and we're going to see what happens. We're going to let it stay this way for a few minutes. Now we're going to get the bowl out and we're going to see if the same thing happens. I think the ball passed through, but I don't think... Okay, does anyone have any idea why the ball passed through the ring?
Yes, it has expanded a little because I heard a noise like collision, kind of collision. So I think it expanded.
Yeah, I think when we did it previously, we did not hear any voices.
Yes.
But right now, when we put it through, they have they're slightly. I think it's slightly expanded, and if we had let it like stay in the water for a few more minutes, I think our experiment would be more. We would have done it.
Yes.
Okay. Shall we let the water boil again, or should we just continue this?
Should.
Okay, we can leave
let's
it.
try to do it.
So okay, till the water boils, we can discuss on why it expanded, even if it was very slightly. So can we give ideas of why that happened?
I think it expanded because there was an increase in temperature, and the molecules in that ball would be more active, and hence they will increase their motion, and that will result in a bigger expansion.
So what I'm understanding is if I heat any kind of metal, the same thing would happen.
Yes, but I don't think the expansion of every substance is the same.
So different metals have different rate of for them to expand, there needs to be, they have different rates for them to expand.
Yes.
Does everyone agree?
Yes, they have different rates of expansion.
The water is boiling, so I think we can try it now. It's still passing through, but it's getting harder to pass. Yeah, you guys need to give it a shot.
You're right.
Yeah, when I tried it originally, it was very easy for me to let the ball pass through the ring. But now when we do it again, it's a little harder and there's something holding it. Yeah, it's more or less accurate, our experiments. I think we've done it, we have proved the theory, right? So now, what if we try it the other way around? Okay, so while we let the metals get back to their original temperature, we're gonna discuss of what would happen if we tried the experiment vice versa. So, earlier, what we tried was, we tried to heat the ball and we tried to see what happened. And well, it wasn't as good, and the outcome was not as good as we expected, but we still saw the difference. So now we're gonna try and hit the ring, and we're gonna see what difference that will make. So I'm gonna ask you guys to give me, your idea of what will happen.
I think I don't think there's going to be much change, and I think it's going to be quite normal, just like we experienced it when it was at room temperature.
But I think it will expand both inwards and outwards, and the ring will expand both.
So you think
inwards and
this?
outside.
So you think the same thing will happen to the ring as it happened to the ball?
Yes.
I have a different idea. I think it will contract. I think they will be expanding at the same time, the outward and the inner part, and as a result, it would make it to shrink. So I don't think the ball will be able to pass through the ring.
Okay, well, the best way to see this would be trying it with an experiment. Viti, can you pass me the boiling water? Thank you. So now both the ring and the ball has been in the room temperature water, so they have the same temperature. And now you've added the ring to the hot water. We're gonna need to stay this way for a few minutes. Okay, so can you describe so for the few minutes? Can you describe how you thought the ring would expand?
Because as we saw earlier, the ball expanded. So I thought they're made up of the same element. So I thought the ring will also expand.
Okay, well, Archie, you see that there will be no change, right? So, well, we saw what happened to the ball, and she said the same thing would happen since they're the same material. So, what convinced you that the ring would stay the same?
We didn't see much change when, just like you said, we didn't see much change when we heated the ball, and even if we heat the ring, I don't think we're going to see much change, and that's what I said. So.
Well, that could be the lack of our materials and all. But see, when we tried the ball, it did not expand as we thought, but it did expand slightly, didn't it? So.
Yes, but I don't think it's. But I don't think the ring would expand and I don't think we'll see much difference.
Okay, well, I think Maliti already described what you thought of the drink, so let's try it. Okay, so after seeing, can you all see it? So, do you think there was any change, whether it shrinked, expanded, or stayed the same?
I think it expanded a little bit.
Me too, and I've changed my mind. It also expands inwards, to both sides, and it expands to this way and also this way.
So, you're arguing with Mahlit?
Yes.
But if it expanded both outwards and inwards, it would make it shrink. It would make the ring shrink, and the ball wouldn't be able to pass through the ring. So there has to be another expansion, I'd say.
Even though we expect the ring to expand both ways, the ring has expanded outwards, and hence the inner diameter has increased by some amount, and that is why the ball was able to pass through more easily than it passed through at room temperature.
So you think the ball has it been easier for the ball to pass through the ring than it has been previously?
Yes.
Okay, then do you guys want to try it and see if that's right?
I still don't agree.
Yeah, you see, earlier we used the fact that we heard a voice when we tried to pass the ball through the ring for the as a reason that it's expanded. So we can't use the same reason for if the ring expanded. So I think we need to try the metal if it was directly connected to the source of electricity, to the source of heat, and see what happens. So then we can make the ball stay in the room temperature. Should we try it again?
Sure. Should we try it now?
Yeah. Okay, I think there's a difference from earlier, but okay, it's still passing through but not like it originally did when it was both at room temperature, right? Mm-hmm. So maybe we should have let both the ring and the ball stay in the room temperature water for more than a few minutes, because maybe the ball still has some heat inside, and maybe it did not come back to its original shape.
But I don't think that's the problem here. I think that the ring has expanded, but it did not expand. But it expanded much more than it was before. That means at room temperature, and the ball has passed through more easily. But we did not see much difference because the ring is originally a bit wider than it would have been ideological.
I have a question though. Are you saying the ring has expanded only to this way? I mean, it hasn't expanded
inwards.
Inwards, yeah.
Yes, it has expanded inwards as well, but expanding inwards is more of contracting. But what we are seeing now here is expansion. So that means that the inner diameter will be much greater than it had been at room temperature.
So what you're basically saying is that there has been expansion on both sides, but the outward expansion has more effect than the inward expansion?
Yes. what we mean by expanding inwards is more of contracting, but what we expect here and what we are seeing right now is not contraction, but it is more of an expansion, and that is why the ball has moved through the ring more easily than the previous experiments.
Okay, does everyone agree?
Yes.
Okay, so then I guess the only problem we had for our experiment not to have worked perfectly is our lack of materials, right?
Yes.
Okay, so our next experiment is also concerned about the expansion of metals, and here we have a bimetallic strip. It has two metals, tin and brass. And as you can see, both are straight and they have equal length. And we are going to see the changes in heat expansion. And we also expect that both metals to expand in a different way because they have different rates of expansion. So let's hit it and see the change.
I think you can already see the change, right?
Can you see the change?
Yeah, this part of it.
I think the upper metal has expanded more.
Yeah.
Let's wake up it and see if we can see a much observable difference.
So then, should we discuss whether or not which one we think would expand more? You gave us two of them, right? Metal and brass.
Mm-hmm.
Yeah,
tin and brass.
Tin and brass. Okay. So which one do you think would expand faster more?
From what I have seen, I think the brass would expand more, but what do you guys think?
I think the brass will expand more. Can't expand more than this given this temperature.
So, are you suggesting that we should take it off?
I think so.
So, do you see any change?
Yeah, I think the upper one has expanded.
I also think that the brass has expanded.
We can even see a gap between the two metals.
Yes.
There's a gap here, and this one's it's a straight line, right?
Mm-hmm.
The one at the bottom and the one at the top, you can see that it's a bit just bigger than it originally was, right?
Mm-hmm.
There's a gap between them.
Yes. So it means that the brass has expanded more and it has increased in length. So this means that brass has a greater heat expansion than tin.
Nice.
So our next experiment is identifying the rate of expansion, the rate of expansion, not the rate of expansion, but heat conductivity of metals, of different metals. And here we have wood, here you have brass, copper, this is aluminum, okay, this is unknown, this is steel, and we have wood here. So we are going to heat the water inside and see the wax at the top melt when the materials are heated. So
that means whichever one melts first, that means the conductivity side?
yeah.
Okay, so while it's sitting, should we guess and should we try to put them in order, which one would get the wax?
Okay, so what do you think, which elements do you think would be more heat conductive?
I'm doing this still.
Still?
Yeah.
Copper?
Brass, maybe.
So we're going to see.
We're going to wait until the wax melts.
Yes.
So then, what do you think differentiates each metal? Like we discussed earlier, each metal has different rate of heat. We have about 6 of metals here, right? Mm-hmm. So we already know that they're gonna for the wax is gonna melt at different times, right? It's not gonna be at equal time. So what causes this? What causes them? What differentiates each metal from each other? Why is one metal called a poor conductor and why is another one called a good conductor?
First of all, I don't think we can say that a metal is a poor conductor. I think all metals are good conductors. It's just that some conduct heat better than the others, but in general, when compared to other materials, metals are good conductors. But each have different rates of conductivity.
So is it due to the material, different, the molecules inside them? Is it due to that they have different rate of conductivity?
Yes, I think it's because of the nature of the substance that some conduct heat better than others.
So it's the nature of the metal that determines the conductivity of it.
Yeah. By the way, we have wood here, so it's not all or not metals, and wood is not metal.
This is taking it's taking longer. We should have put less wax like this.
Or it's taking the water
too longer to work.
Maybe.
Yeah.
This is taking a longer time, so why don't we discuss the questions on our worksheet, so the water balls?
Yeah, that's a good idea.
Okay, I'll read the questions. Number 1, what are the heat transfer processes?
Okay, so there are 3 heat transfer processes: radiation, conduction, and convection. So let's start from conduction. And conduction is mostly observed in solid, and there is a direct contact between the materials. For instance, if I touch a hot stove, heat will be transferred from the stove to my finger. directly, so we call this conduction. And the second one is convection, and what makes convection different from conduction is the first, convection is mostly observed in fluids, and the other difference is during convection the material will also be moving. For instance, in a warmer day, when the temperature rises, the air near the surface of the earth will be warm, and when it's warm it will have less density, so as a result it will rise upwards, and then the cold place will move downwards, and as it gains heat it will also move upwards, and the cycle continues. So this is what we call convection. And the last one is radiation, and radiation is the transfer of heat through electromagnetic waves. And as we know, electromagnetic waves don't need a material medium to transfer energy from one place to another. And a good example for this would be the sun. And the heat that we get from the sun is due to electromagnetic waves, so it is a type of radiation.
Okay, and the second question is there any application for pure heat conductor?
Yes, there are many applications for pure heat conductors. For example, in dishes, we don't want our hands to get burned when when we are cooking. So the handles are mostly made of wood or plastic. We can see another application for pure conductors. Because the metal here is a really good conductor, and because we don't want our hands to get burned, here we have wood, and the wood is also a pure conductor and lets our hands be safe because we can't get through the heat. And we can also see other applications for pure conductors in our blankets and coats, because they preserve the heat we have, and they don't let the heat escape our body. And heats and blankets and coats are good applications of pure conductors. So what about good conductors?
I think we can take ammonia as a good conductor, and its application is for cooking foods. We need good heat conductors to cook our food, so we use ammonia for cooking foods. Okay. Are there any more questions? Yes. Why is it preferable to hold black umbrella during hot summer days?
I don't think it's actually preferable to hold black umbrellas. I go with white. Because like how I see it, black is a color known for like letting heat through, but white it only lets it bounce and reflect back. White only lets it reflect back. So if you're holding the umbrella, a white umbrella, that means the heat would not reach us. But if you're holding a black umbrella, then it's only obvious that the heat will reach us as well.
You have anything to add? So that means we are left with ours.
When the wax on copper is starting to melt, so which means copper is the best conductor out of these 6 metals.
5 metals.
6.
Yeah.
6 different objects and 5 metals. Okay, so copper is the best conductor because, as you can see over here, it's melting.
Yeah.
Yes. So who expected copper to melt?
I think we predicted that.
I think the steel is starting to melt. The wax on the steel is starting to melt as well.
The wax on the aluminum is also melting, from what I can see.
So I guess the first one was copper.
So which one is the second one? Aluminum or steel?
Steel.
Are you sure?
Yeah.
So the wax on copper has completely melted. No. So it must be a very good conductor.
Yeah. So now we're left with the brass, the unknown item, and the wood. So which one do you think would come next?
Not the wood for sure.
Yes. Okay, then what about the unknown?
So
we don't
it's
see
between
that.
the brass and the unknown meter.
Yeah. I think the unknown method is starting to melt as well.
Actually, why don't you stand up there too?
It is starting to melt, but it has not started completely. Yeah, after a few minutes, it will melt.
What about the brass?
Right.
I don't think the
Yeah. But at the lower side, it's starting to melt.
So here, the steel started melting first, but now, as you can see, the aluminum has less wax on it. So I guess the amount of wax put on the both metals was not equal.
Or maybe aluminum has a greater heat.
Conductivity. Than steel.
Yeah. See, it has completely melted.
Yeah. I mean, it's known for being a good conductor, so it wouldn't be surprising if it's better than steel.
So the first one is copper, and second is aluminum, and I guess we're waiting for steel now.
No, I think the steel has melted a bit.
Yeah, the steel has started melting, but not as good as the aluminum and the brass. I mean copper. I don't see much change on the brass either, but. I think the unknown material is melting faster.
Yeah, I think it's the third most heat conductive one.
And then the fourth. Yes, we have copper, then aluminum, then steel.
But I don't think
The steel is still like.
the unknown metals.
So I think the unknown should come first.
Sorry.
Third, I mean.
I think the wax on the brass is melting.
In the brass?
Yeah.
I think the water has also reached its boiling point, and it's being changed into steel. So the wax on the unknown metal has completely melted. So it's between the steel and the brass.
Yeah.
I think the brass comes first.
Yeah. The steel started melting long ago, but the brass seems to have been melting faster. Okay, so as we can see here, all the other 4 of the metals have completely melted the wax, but we're left with steel and the wood, and we have already concluded that the wood should be last because it's not even a metal. So the first one to conduct was copper, so obviously, it must have the highest rate of conductivity than all the rest of items. The second came aluminium, and then was the unknown metal, and then the fourth one was brass. And the steel has steel wax on it, so I guess that should be the quick one, and then wood would be the last.
Okay. So let's summarize what we did today. But before we do that, I have a bit of doubt about what we did earlier, and and from the book I read earlier, I remember that white lets some light through while reflecting it back. So if we hold a white umbrella, it means that we will feel the hotness of the atmosphere. But if we hold a black umbrella, because it withholds heat, it means that the umbrella itself will be much hotter, but we won't feel hot because conduction never acts in the downward direction, but it acts in the upward direction. Yes, convection, sorry. So it means that we won't feel hot, and we'll feel warm, but not hot, and that is why I think that black umbrella is more convenient for hot day.
So black. So like when we think of it, it's black is not for like black clothes and stuff are not for getting people hotter, and so that's only because it's like directly connected to the skin, not because because of water.
Yeah. So I think that's the explanation for it. So Malik, why don't you conclude today's experiment?
Okay, so today's experiments were mainly concerned with the effects of heat, especially expansion. And we were during our first experiment, we were able to see the effect of heat, and we observed that metals expand when they are heated. And we tried that using a ball and a ring. And we also tried the same experiment using a bimetallic strip. And using a bimetallic strip, we were able to observe that the bimetallic strip bent when heat was applied to it, because a bimetallic strip has 2 different metals on each side, and these 2 different metals have different rates of expansion, which cause the bending. And at last we were able to observe the conductivity of metals. And earlier we already know that metals are good conductors, but this doesn't necessarily mean that they conduct heat at the same rate. So we were able to identify which materials were better heat conductors than the others.
Okay. So Betty, you have anything to add?
About nothing to add, but I just realized that 2 of the materials we used to check heat conductivity are those which we mentioned earlier as one poor conductor, which is wood, and the other good conductor, which is aluminium.
Yeah. So that is it for today.